Recording has begun.
Okay. Okay, thanks, Will. Appreciate it. All right. Hey, Simone, if you don't mind just jotting down, I'll give you just one there, your thoughts about how the control charts unit is going so far. And for the online students, if you want to write me an email, I'd love to hear from you guys. How do you think it's going so far? And hopefully I provide clarity this morning, in which case maybe you'd change your response by the end of the lecture period. But I'm just curious to hear, are we going at a good pace? Does this make sense to you? Does the math seem doable? Are the examples I'm giving you good enough? And what I'll do is same thing with the variable control charts assignment. I'll post it very soon, and then you'll get instant feedback once you submit it, and we'll give you 3 attempts or something like that. So, but that's the goal. I think everyone did great with variable control charts if you tried and used all 3 attempts to figure out the right answer. That's all that matters, is if you eventually get the right answer. And if you want more attempts, just let me know. So that's where we're at this morning. So here's a picture. For fall break, what I did is went up with the family on Friday morning up to Ashe County, which is that very top corner of the state by Virginia and Tennessee. It is beautiful country up there. The Appalachian Trail kind of winds through there with, there's a peak called Allen. There's these wild horses that roam the mountainside up there, and my in-laws have a property up there. Anyways, yesterday on the way home to Raleigh, we stopped in West Jefferson. There was a very nice agritourism farm. They had one of everything. Hay rides, pumpkin patch, barbecue sandwich was delicious. If I could remember the name, I would endorse them for you, but I forgot the name. Anyways, we had a great time, and on the way out, of course, we got our obligatory pumpkin. And I'll be doing this again on Friday. Just as a reminder, Stephanie's going to be here teaching you the lab on Friday. I'm jealous because I want to teach that lab, but if I don't go on this field trip, I'll be a bad parent. I'll be the only parent in the whole school of probably 100 kids who doesn't have at least one parent there. My wife's out of town at a conference this week, so I'm solo dadding it right now. So anyways, why am I talking about pumpkins? Well, because it's perfect for this lesson on attribute control charts. You've all seen pumpkin before. Chances are everyone has picked a pumpkin, and if you haven't, it's never too late to start. It's a fun tradition. You can decorate your pumpkin, you can carve your pumpkin, you can eat your pumpkin, you can make a puree out of your pumpkin and put it in your pie or beer or whatever you want to do with it. And I found this picture online. I must admit, it's not my picture. I should have taken a picture yesterday, but I had my hands full. So thanks to the FayettevilleFlyer.com. This was very representative of what we saw yesterday afternoon. You see a big pumpkin, and that was the big point of negotiation. My daughter, who's the only kid out of the 2 who can talk, poor Walter didn't get he didn't get his opinion in on which pumpkin to get. But so Lucille said she found the biggest one they had. I said, you can share one with Walter, or you can each have one. So we talked Walter into wanting to share this really big one, right? Anyways, looking at a picture of pumpkins like this, you can see some of them look more perfect than others. It's an agricultural commodity. It grows on a vine. They don't grow underneath the dirt like potatoes or anything. They grow on top of the dirt, right? So they're subject to the weather, pests, and obviously for the FayettevilleFlyer.com, they picked out the best pumpkins they had, right? These are some pretty nice looking pumpkins. But even still, I can see from up front, there's a little scratch on this big one, 2 or 3 scratches. And if you've been out to a pumpkin patch before, you've seen those that just get left behind. They're just moldy and nasty. If they're a perfect one, those ones go pretty quick, right? Families get out there, especially early in the season, and like this is like prime time to go get the perfect pumpkin because, you know, we've got 2 more weeks before Halloween. Good luck. It's like getting a Christmas tree on Christmas Eve, right? You kind of get the Charlie Brown Christmas trees if you do that. So anyways, you can just think through, and actually some people might like, anyone like these ones on the bottom left? I started acquiring a taste for them lately. They look different. They look kind of artsy, but they don't look like your beautiful, just all orange pumpkins. So it kind of depends on the eye of the beholder. What's a perfect pumpkin? But you can think for yourself, are you going to decide that this orange one on the bottom left with all the orange, looks like warts, doesn't it? And same thing with this dark one right here. Is that defective or is it not? And as a class, if we just said, yeah, we're targeting a perfectly round orange pumpkin with no scratches, no mold, no warts, that could be our definition of the perfect pumpkin. And then from there, we can think about all of the attributes that might be defective. And we can go from there and think through, if you were a pumpkin farmer, what type of a control chart would make most sense for you? And as a reminder, we can draw a line right here, because for the top 2, we're interested in how many out of all of these are defective. We don't care what makes them defective. It doesn't matter if they have a scratch or if they're moldy or if they have a wart. That's all we care about. We just want to know how many are going to get left behind or something like that. Whereas if we are concerned about the C, the count of nonconforming units, or U, which is basically the same thing, we're just going to use U for when the sample size varies, then we're going to be, on a pumpkin like this, counting how many nonconforming units there are. So for this one, I would count 1, 2, 3, just based on the naked eye on this Google picture right here. So right there, our C would be 3. Good luck counting all the warts on this one. I don't know how you would do that. The count of that, if you said a wart was a nonconforming unit, would probably be 200 or something like that. So it's kind of a weird example for that case. But let's say, hypothetically, how many pumpkins would you guess are in this picture here? 1, 2, 3, 4, 5. I don't know, about 25 or something like that if we had, oops. If we had 25 pumpkins, and let's say the defective, let's just guess that we have 5 that are defective, then our P is simply going to be 5 divided by 25, which is 5 times 4, 0.2. Is that right? Yeah. 0.2. Our proportion nonconforming, 5 times 4 is 20, divided by 100. Yeah, that's right. So we have 20%. That's our proportion nonconforming. Does this make sense? Okay. I was like, do I share this example? We already kind of did this last week, but then everyone's getting back from fall break. It probably wouldn't hurt if you didn't make sense out of the M&Ms when we did this. Maybe when you go pick a pumpkin, you can tell your friends and bring your control chart notes with a blank piece of paper and your computer with Jump on it while you're on a hayride. And there you go. Okay. So this is a very nice slide, I think, that will help you out. And this morning, my plan is to just make sure you understand these two. If we get cruising, I might pull out the next slide deck and we'll launch into C charts and U charts. But right now, let's just focus on how many out of the lot, sample, are bad or good. We don't, at this point, care what makes them bad. We're not going to count how many nonconformities there are. We're just going to count out of a pumpkin patch how many are bad. Which, if you're a pumpkin farmer, that means money, right? And for you, you can, as we launch into this, maybe think through what would be some products in your industry that it would make sense to apply this methodology to. Obviously, on the food side, we have agricultural commodities, and it is a real deal. When I worked at the potato company, Ore-Ida, doing French fries, tater tots, hash browns, we looked at data every day. Potatoes are coming out of Oregon, potatoes are coming out of Idaho, potatoes are coming out of Washington. This farm in particular, which has 3,000 acres, is known for bruised potatoes, and you could count that. You could even go on. They had these amazing cameras set up that sampled even the French fries. They would count how many French fries had a bruise on them or a nick or a cut or something like that. So food is a very nice example because we're working with agricultural commodities. But on the bioprocessing side, can you think of some products that would have attributes that could be conforming or not? I'm asking because I'm not a bioprocessing scientist, and about half of you are in the bioprocessing program. Anybody? Will?
You could do it off of like packaging for certain things.
Yes, perfect packaging. I was wondering if you would say that. Yeah, because you're working with some very important products that need packaging with integrity, and if that packaging goes bad, yeah. So let's ask. We did confirm someone from Fujifilm to come talk on the bioprocessing side, and I'm still working on another guest speaker. So we'll. I was driving past. Did you realize Grifols is off the interstate on the way out west? Let's see if we can get someone from Grifols. It seems like I had someone from Grifols a couple of years ago. Anyways. All right. I'll be in touch. That'd be great to get someone from Grifols because they're a big bioprocessing company. Okay. So, as you know, in this class, we like to break things down. You know, there's this many steps to make a histogram. There's this many steps to make a control chart. And the same steps that applied for variable control charts are going to apply to attribute control charts. Step number one, we have to decide if we're talking about pumpkins or whatever, what is our quality characteristic that we're concerned about? For pumpkins, we could just say, does it have a bruise on it? Or we could say, does it have a scratch on it? Or we could say, is it moldy? Or we could say, is it any of those three? In which case it's going to be non-conforming. Okay? And then just like we did, whether you realized it or not, for the variable control charts, we determined the subgroup size. And there's a little trick here, little method to figure out if you don't know, like if you're starting from scratch, you're solving a quality problem on your own, you're going independent, and you're like, I don't know what my sample size should be. I've got thousands of pumpkins. I've got 5 farms. What do I do here? This is the formula that we can use, and we'll have an example in a couple slides where we apply it. But just briefly, we're going to solve for n. What is n? You know, no one told you n, no one gave you data. And then we need to get an estimate of the p-value. I think a better word here would be proportion of proportion. What is the proportion nonconforming? We're going to simply multiply that times 1 minus p. And then we're going to look up this z value. So if we want a 95% confidence limit, we're going to punch in 1.96. And you'll have these slides. And we're going to calculate E. And what is E? It's the desired precision times an initial p-value. There's a bit going on in this formula, but if you just break it down to these 4 things, it's simple algebra. Okay? So the desired precision, in the example I have coming up in a couple slides, you'll be given the desired precision. And you know what precision is, right? It's like we were saying, if you have a dartboard, you know, this is more precise than this. So you'll see often it's like 5% precision, 10% precision, and we'll use 10% for the example coming up. So we're going to, the key is for E is not desired precision. E is desired precision times the initial P. I always have a couple people who just punch in the desired precision right here, and then they're done. And they forget to calculate the initial P. And to get that initial P, we're just going to get at least 50 samples and count how many are bad in that 50 samples. Does that make sense? So pretty simple. So we'll have an example coming up for you. But just looking at it from a 40,000 square foot view, we've got these 2 steps. We've got to figure out what we're concerned about, figure out how many samples we're going to take, and we're going to determine how to sample those. Eventually, we'll collect our data. And ideally, you have at least 25 subgroups on your chart. Remember, subgroups is the x-axis. If this is our center line, these are our control limits subgroup. So you would have up to 25 observations. Okay? It's hard. And why do we say at least 25? Well, because you can't really see a trend until you get enough on that x-axis. It makes sense, right? If you only had 5, you would not really get a chance to see 2 proportions or a steady increase. Okay, so it takes some work to make a control chart sometimes. To get that data, you sometimes got to roll up your sleeve and go into the plant and get the data yourself, or maybe you'll be lucky and have a quality control lab that collects that data for you, or even better, you've got an inline sensor that just automatically does it or something like that. But anyways, at last, we're down to our handy-dandy central line and control limit equations. And just eyeballing these, I don't think you have a whole lot of experience except for the study ahead questions. They look pretty simple, right? Just basic math. You see the magic number 3 there again. Remember, it's always going to be about plus or minus 3 standard deviations away from the process mean. And that wasn't inherently obvious with the variable control charts because we worked with the constants, but with the attribute control charts, it's definitely right there. For the variable control charts, you had those constants, D2 or whatever, and the people who designed those, these are supposed to get you basically the same result, plus or minus 3 times the standard deviation. Okay? And notice how I actually prefer working with the attribute charts because the math is so much cleaner. You don't have to look up a dang constant out of a table, right? You just need 2. You only need 2 items: your p-bar and your sample size. Although it will get a little bit muddy, as I'm going to show you this morning, if you have a sample size that is not constant. Because, as you'll see, you kind of got to calculate the control limit for the first observation if the sample size is 50, and then you have to do it again if the sample size is 55 on the second subgroup. So we'll get experience with that this morning. But let's start out with an example. We have a soft drink company, Coca-Cola or Pepsi, something like that, or some local bottler. They're monitoring quality of their beverages in terms of clarity. Clarity is important, right? People like to look at a bottle and see straight through it, see how bright it is. Samples are visually inspected and marked accept if the sample is translucent and reject if the sample is cloudy. I don't know what would make soda cloudy. I guess there could be a bunch of different things. It depends on what it's made out of, right? If you had like a cherry soda, maybe you didn't filter out the cherries good enough or something like that. Anyways, previous data has shown the fraction of cloudy bottles per lot is 0.05. So our first question is, how large should the subgroup size be for a 95% confidence interval and a desired precision of 10%? So I think we have everything we need to figure out what our subgroup size should be. What's another term for subgroup size? Sample size. I'm sorry, but it just is semantics. You deal with this in science all the time. You're like, why can't you just call it sample size all the time? Why can't you just call it subgroup size all the time? But that's just the reality that we're living in. You go back and forth. So, but with experience, you'll just pick it up. Okay, so anyways, we want to solve for n. With any luck, my coffee's been working this morning, and I can remember that formula. Didn't it say n equals p times 1 minus p times, wasn't it just the z alpha divided by 2 times e, where e was p times desired precision. Don't worry, I'm going to double check. We'll go back a couple slides. Okay, right here. Yep, looks like we got it. Okay. Okay. So, first question. Do we have P? What is P? 0.05? Yep. Equals 0.05. You know what 1 minus 0.05 is? 0.95. And I'm old school. You guys don't put the 0 in front of the decimal, do you? At some point, the public schools stopped teaching that. But you'll see me do it. I don't know why I mentioned that. We need to look up z of alpha over 2. And I just know it because I practiced it before class, and I just looked at it when we looked at that slide. It's going to be 1.96, which is right here. I've written over it now, but this is 95% in the second column. Can you see that? We're looking over here, 1.96, okay? And we need to divide that by E. And here we go. Don't make this mistake of only punching in, the desired precision. We got to multiply these two. So we're going to put in 0.05 times 0.1. Okay? So I'm going to do it on my phone, but if someone wouldn't mind double checking, 0.05 times 0.1 is 0.005, so I'm going to divide 1.96 divided by 0.005. That's 392 times 0.95 times 0.05. And I get 18.62. can't have a fraction of a sample, so I would just round up to 19. Did I get that right on my calculator for whoever double-checked me? Cool. Perfect. Okay. Very nice. Very nice. So we've just accomplished step 2 in constructing a control chart. Remember, step 1 is figure out what you care about, and then step 2 is figuring out how many samples you need. You'll see on the next couple of slides they have way more samples than 19. It's like in the 200s. But this just tells us if you want a 95% confidence interval, and you know what confidence interval means, right? It is what it sounds. How confident do you want to feel? Do you want to feel 95% confident or 99% confident? And if we look at that table of values, you can see the Z value gets larger as we go up in confidence. And it makes sense that you would need more samples if you want to be more confident, because this Z value is in the numerator. So if the higher, like if you wanted a 99% confidence interval, Z is actually 3 or something like that. So you would need more samples. So depending on how risky your operation is, you know, how risky a faulty attribute would be, you would take more samples. Okay. Everyone with me so far? How to calculate sample size if you had to from scratch? Okay. So we just answered this one, 19. And next, we're going to calculate the central line. Okay. So here's what a P-chart data set example would look like. We have how many subgroups? 25. Now let's look at the second column. You understand this is split in half, right? Just to make it so you can see it on one slide. Ideally, we would have shown 13 through 25 underneath 12. Anyways, the second column is N. Notice how they go from 225 to 200 to 275. It's not a constant sample size. And that's why we're working with the P-chart instead of the NP chart. Recall if we go back a few slides, right here, we're going to use NP if we have a constant, but we're going to use P if we don't have a constant sample size. Okay? That's the only difference between the concepts of P versus NP charts. Okay. Now, what is this next column? Number non-conforming. Well, let's just take an example. Find an easy one here, maybe. I don't see any round numbers. Well, then we'll start with the first one. So for that first subgroup, we inspected 225 bottles of soda. Could you imagine that? That's a lot. I guess that's when you want to be being paid by the hour, right? It would take some time to be doing that. Anyways, we had 22 out of 225 non-conforming. Does that make sense? Just have a big table full of bottles and 22 are bad. So you see the math of how to get the proportion non-conforming, which is the third column here. This is P. Okay. So, and if you don't trust me, you can do it for yourself, but we're just going to go P equals 22 divided by 225. 22 on my calculator divided by 22 divided by 225. It's actually 0.098, but you get the point. We rounded up for this example. So that's P. That's how to get P. Individual P, not the average P, not the P bar. But let me take a step back. I'm kind of going slower on this than I do usually because every year I get some people who are confused about what's the difference between P and NP. So that second column is NP, number nonconforming. So if we look at our formula here, notice how for this P bar, we're going to divide the sum of NP by the sum of N. And we're going to do that for the individual P as well. God, it's so awkward to talk about P so much. N, P. All I can think of is my 2-year-old potty training at home. But for the individual P, it's going to be the same thing, except it's not the sum, it's just the individual. And that's what we just did. We took the 22, this was 22 divided by 225. Okay? So it's really not complicated math. It's just like some things in life. You just got to make sure you got everything organized in your head, and you just break it down to the simple steps of what am I thinking about here? Is this right? It's very meticulous. I'll put it that way. Simple, but meticulous. Okay. Dun, da, da, da. So if n was constant, we wouldn't need this third column. We would just chart the number nonconforming, NP. We wouldn't divide it by n because there's no need to standardize it. But this example is a pain in the arse because its sample size is constant, and I'll show you why that's complicated if you have a unconstant sample size here in a little bit. But let's see here. I'm going to clear everything, but just as a reminder, this is NP and this is P. I'm just really pumping the brakes on this one because every year I get, it's like a third of the class who's, I'm just like, it's on the same table. You realize that, right? But I, in the past, have kind of breezed through that example. Okay, but you see where we're going with this, right? We need to calculate P bar. You could do that, right? How do we calculate P bar? Well, we're just going to add up all of these P's, 0.1 plus 0.11 plus 0.06. I'm not going to do it in front of you because there's 25, because you've done this before with the variable control chart. So are you fine with me if I don't actually calculate it for you? We're just going to sum up NP divided by N. So it's going to be all of these added together divided by all of these added together. Okay. I always struggle when we get to this point in the class because I'm like, do I calculate it in front of you in class? I don't know. We've already done this with variable charts. You see that it's the same pattern. Calculate the P-bar and then calculate the central lines. But don't worry, we'll have plenty of practice examples coming up with the case study. Better cheddar. Okay, everyone with me? And you, based on that P-bar, you know where we're going with this. We're going to calculate those control limits. Easy math. Easy peasy. That's high school math, right? If not, are they teaching that stuff in middle school now? I don't know. I'm pretty sure to get into NC State, you had to be able to solve a problem like this, right? Put it that way. That's what I'm going to use as my litmus of whether I need to practice something in front of class or not. Because it's nice to be able to cover more ground by not doing simple calculations like that, but instead by showing the complicated ones. Okay, and then you could, if you had more time, crank out a control chart, a P chart, and identify any trends, right? And again, we've had, I think, enough experience doing that with the variable charts. We'll get more experience with these attribute charts, but it's hard for me to just slow down and every single example look for trends in the chart because it'll take till May to get through the class anyways. And I believe if you want to do this on your own time, I set this up in the spring semester. I think it gives you instant feedback. If you want to, because we didn't actually calculate these numbers on our in-class time. If you want to, in your own time, do it. I'm pretty sure I set this up so it gives you instant feedback, whether you got the answer right or not. And I highly encourage you to do that. Why not? You can do that while you're on your way out to the pumpkin farm. So you can see what is the lower control limit for the first subgroup. Okay. For the second subgroup. So I would definitely do that. It'd take 15 minutes. Okay. All right. So, but the thing I want to end on is, what do you do when you have an uneven sample size? In other words, like on this example, we had 225 samples on the first subgroup. We had more or less on every other subgroup after that. So there's two or three different approaches to this that I'm going to show you. The good thing is when you do it in a computer program like JMP or Minitab, it chooses what I think is the best method, and I'll show you what that is. But let's just look through. Okay. So here's one option. One option is, and I think this is my favorite, because it makes interpreting the control chart so much easier, whereas the next method, you kind of have to take every control limit and observation with a grain of salt, and you'll see why in a little bit. With this one, you don't. This one's funky, though, because you'll end up with a control limit that looks like this. Upper control limit, lower control limit. Isn't that weird? And this would be your center line. Center line. And the reason it looks like that, actually, it could also look like this, I suppose. Like shark teeth. Those could be the control limits. But the point is, you calculate the control limit for every single observation. You do it for the lower control limit, and you do it for the upper control limit. It makes sense, right? Because n is what is varying. Okay? So, like I said, the computer, if you have the right program, will just spit it out for you. It's always good to double check the computer's work, of course, but that's one way to do it. It's just a lot of math. But if you're working in Excel, you can set up the formula in the column to the right of the table, and once you get it right, you can just kind of drag down so it copies all the way down, if you know what I mean. Okay. The other method is to basically take the average of whatever the sample size is and put that wherever n is in those formulas. And I have some examples coming up. So let's move on to fish sticks. A company manufacturing fish sticks samples an average of 300 fish sticks every day. Sign me up. I love fish sticks. Get some big bottle of ketchup. Why not? However, the number of fish sticks examined for nonconformities per day varies. Data for the previous 25 days is shown below. Why do we always have 25? I guess that's because it's the minimum subgroup size recommended, so you can see a pattern. Calculate the central line and control limits for the first 3 points. So here's an example where sample size of the first one is 313, and it's 295. Yeah, Chris.
So why wouldn't they sample the same number every day?
Good question. Why would you not sample the same number every day? If I was in charge, they would. but you're not always in charge, and there's always just weird things that happen. They were told to get 300. The first day they overachieved. The next day they didn't quite get enough, or I don't know. It's just weird out there. But yeah. And another possible reason could be, I don't know how much you know about like random sampling, but if you've taken like a class on experimental design or something like that, like the way random sampling works is you punch in the computer like, this is my parameters for this sampling program. The random number generator, well, doesn't always give you 300 in certain experimental designs. It'll say, today get 313, today get 295, today get this many. And I don't know enough about it to explain why. I just know enough to be dangerous. But I'm like you. I'm like, why would you go through all this extra work? Why couldn't you just go in with 300? So it's a fair question. But let's just look at this example. So here, I've given you an example with these fish sticks. Unlike the previous one, where if you wanted to practice this on your own and see the actual solution, you could see it in the PowerPoint slides. But I'll remind you, in the previous example, you can do it in Top Hat and enter it in, and it'll tell if you're right or wrong. But in this case, how did we get that p-bar? Well, we're just adding up all of these p's, np's, 19 plus 14 plus 17, divided by all of these n's. So 305 is, how many we had in this column, and 7,612 is how many we had in this column. So that gives us p-bar. So now we drop 0.04 plus or minus 3 times p times 1 minus p divided by n. Okay, so the big question, though, is what do you put for n? Okay, but for this first observation, for the first subgroup, we're going to use 313 for n right here. So that gives us the control limits for the first point. And the control limits will be different for the second point and the third point. And this is what it looks like for you. Okay? So see how it looks wonky because you don't get that straight line that you saw with all the variable control charts. But you know if it's out of control or outside the control limits in this case. In this case, we don't see any outside the control limits. However, let's just have a brief chat about any patterns you might see. If someone said, here's our control chart, and they said, we don't have any points out of control. Now that you're taking this class, you would say, yeah, I don't know. Let me think about that. I agree there aren't any outside the control limits. But let me see if I can find any patterns. Anyone see a pattern? If so, what pattern do you see? Do we have two populations? Not really, because we don't see a bunch hugging the top line and a bunch hugging the bottom line. Do you see a cycle? Yeah, maybe. It kind of goes down and then, yeah, I don't know. What other patterns have we talked about? Do you see a steady increase? Not really. Steady decrease. Do you see a jump? Yes. At subgroup 7, it jumps to subgroup 8. That's how I would read it anyways. Obviously, it's subjective, but by now I've taught you the handy-dandy Westgard rules and the Western Electric rules. So if you were using jump, it would just, boom, put a number. You know, if it's test 8 and you get a positive for test 8, you can look that up. So you don't have to eyeball it as much. Okay, so here's to illustrate that when you have a bigger n, the control limits are tighter. That makes sense, right? if you just kind of think about it conceptually. Whereas if you don't have as many samples, the control limits are farther apart. Okay? Okay, so they can be hard to, yeah, that's a good point, that first bullet point. So if you were to show this to a bunch of hourly workers who never cared to learn about control charts, and they're just told, all right, in your 9-to-5 job, you have to do this. You know, they care about quality, but this is kind of a weird one. It's like up and down and up and down. So I'm with Chris. I would just make one where the sample size was the same and those control limits were always the same. It was a straight line. Okay, you can't calculate varying control limits ahead of time. Why? Because you need to know how many samples were in each observation so that you can put it in the denominator. Okay, there's two ways to minimize effects of subgroup size. You can make control limits for the average subgroup size or for the different subgroup size. And we have an example coming up. So if instead you wanted to be, maybe not go through all the work, or you didn't have the computer to punch in 295, 311, put in that n in the denominator for all 25 subgroups, you could just put the average n in there. And so if the total n was 7,612, because remember, this equals the sum of NP divided by the sum of N. So if sum of N equals 7612, and there are 25 subgroups, what is N bar, basically? What is the average N? How would you get that? What would you divide in this case? What goes in the numerator? We have everything we need to solve the problem. Tia? Yep, 7612 divided by. I see where you're going. Let me re-ask it then. If we want to know the average N for all 25 subgroups, because this 7612 was for all 25, we're going to punch in 25, right? So that's how you would get N bar. And then whatever this is, you would punch that in the denominator instead. Got it? So it's just depends on your philosophy. Would you rather, are you one who wants to get every single observation, so you just, you have more control over the control chart, or do you want to just kind of punch in, we just did this formula right here. Do you want to just punch in that average N, and this is what this control limit would look like. Same story, fish sticks. But now, instead of a control chart that looks like this, we have a control chart that looks like this. Looks cleaner, but now you're going, yeah, I don't know. Let me take it with a grain of salt. That first observation looks like it is outside the control limit. Let's just figure out real quick, what was the average N? 7612 divided by 25. So average N is 304. So now you're going, well, I used that, but what was the sample size for the first subgroup? Do you remember? Yeah, 313. Yeah, 313 right there. So you're saying, but that N was 313. Oops, 313. So that's 313. So now you're going, well, but you see where I'm going with that? Because this is not the true control limit. It's just it's the average. So now you have to just, you're eyeballing it, but you're going, well, what was the, because if it's bigger or smaller, it's going to mean whether, if if the sample size was bigger, then it's going to be closer to the center line. If it was smaller, the control limit was actually, in reality, farther away from the control limit. So now that you understand this, we're in good shape if you do understand it, because it'll be the same thing when we get to the C charts. So when we show up on Wednesday, we'll have some NP chart examples, which are a lot easier, and then we'll move into the count charts. So, all right. That's it. And if you filled out one of the cards, if you wouldn't mind just leaving them right here or on that desk back there, I'll pick them up. Thank you. Appreciate it. I'll just put a pile right there. Thanks, Tia.
So you said you confirmed something?
I think so. I need to go back in my email, but she wrote back. So I either confirmed her or rescheduled her. But she was excited, I think. So
Yeah, that's cool.
yeah,
And
thanks
she's
a
on
lot.
vacation this week, so I haven't heard from her this week about it, but
Gotcha.
yeah, that's
Cool.
exciting.
Yeah, have a good one.